All right. Hello, everyone. This particular video is going to help you out with your GELO assignment, okay? And it's going to build on the stuff from the previous videos, but a little bit of this material will also lead into the next set of videos, or the videos you'll watch right after this. So the main thing I need to introduce for your GELO assignment is a type of diagram that builds on the properties that we talked about in the previous videos. Specifically, we were learning a lot of properties of stars, luminosity, surface temperature, and radius, which in this case stands for size, right? So I'm going to focus on those three properties: luminosity, surface temperature, and size. And the type of diagram that we're going to talk about that's related to all three of those is a diagram called the Hertzsprung-Russell diagram. Hertzsprung-Russell diagram. And you don't know how much I had to practice in order to say that right. And in case you want to know how to spell it, here we go. Here we go. It's the Hertzsprung-Russell diagram. I even wrote this ahead of time because I did not trust myself to spell it correctly in real time. So here we go. What is a Hertzsprung-Russell diagram? Well, mainly it's a type of graph that works very similar to just a regular old graph, but it's a graph of specifically luminosity versus surface temperature. So what is a Hertzsprung-Russell diagram? It's a graph of luminosity versus surface temperature that's trying to tell us something about stars, okay? So we use it to study stars. Now, because we don't want to have to say Hertzsprung-Russell diagram all the time, Hertzsprung-Russell diagram, Hertzsprung-Russell diagram, Hertzsprung-Russell diagram, even if you have some practice, it works. But usually astronomers will just abbreviate this and make it the HR diagram. So HR diagram and Hertzsprung-Russell diagram, that's the same thing. Okay, now I've started to draw one right here, and I'll explain how this works. Here's our HR diagram. Let me zoom out just a little bit. There we go. So just like I said, it's a normal graph. Here's our two axes, the y-axis and the x-axis. And on the x-axis, or horizontal axis, we have surface temperature. Okay, that's surface temperature down here. And over here on the y-axis, or vertical axis, we have luminosity. Okay, luminosity. Remember, luminosity is the total amount of light that a star makes per second, technically for any object. And surface temperature is the temperature of the surface. That one's pretty easy to understand. And this graph has a little bit of a wrinkle to it. Check this out. First of all, the luminosity does increase as you go towards the top of the graph. Okay? So the top of the graph has a very high luminosity. So we can think of these as bright stars. Everything along the top is bright. And the very bottom of the graph is a low luminosity. So we can think of these stars along the bottom as being relatively dim. And of course, we're talking about in terms of the amount of light they make. Bright at the top, dim at the bottom. So you get brighter as you go up. On the surface temperature axis, though, it's a little bit backwards. So instead of increasing as we go in the normal direction, it actually increases as we go to the left. So to represent that, I'm going to draw an arrow here going in this direction. There we go. So what I'm saying here is that the surface temperature will get hotter as you go in this direction. So this is your hot side. This is your cold side. So any stars that are right here on the graph, all over here, these would all be cold. If you had any stars on this part of the graph, they'd be cold. So the right side of the graph is cold. And any stars that show up on this side of the graph are hot. Okay? So again, for luminosity, the bottom is dim, the top is bright. For surface temperature, the right is cold and the left is hot. Why do we have that kind of flipped? I'm honestly not 100% sure, but that's just traditionally how we set this graph up. I believe it has something to do with putting the spectral types on. So if you don't remember what the spectral type's on, watch the last 2 videos before this one. But essentially, when an astronomer tells you the spectral type of an object, one of the things they're trying to tell you is how hot the surface of that star is. And this is your O, B, A, F, G, K, M, right? And if you remember, O was the hottest stars, and M, that was the designation for the coldest stars. So if we said on this graph that the left is hot and the right is cold, then O would be over here and M would be over here. So I can put down here O, B, A, F, G, K, M. And so that means that any star that ends up above the O would be an O, and it would also be hot. Any star that ends up over the G would be sort of medium, and M would be cold. These would all be M's over here. Okay, now let's think about this. Here we go. What would a star be like if it ended up right here on the graph? If we took the surface temperature and the luminosity of a star and we popped it on the graph and it ended up right here, it would be very hot because it's above the O, and it would be very bright because it's at the top of the graph. A hot star that's very bright, that's not an unexpected thing. We expect hot stars to be bright. That would be an unsurprising star, okay? How about down in this corner? What's this one like? If you're down in this corner, well, the temperature's very cold. You're over above the M's, so this is a cold star. But what's the luminosity like? What's the luminosity like for this corner? Well, if we go over, if your star was right here, it's at the bottom of the graph, so its luminosity would be very low. So stars in this corner of the graph are cold and dim, which again, not very surprising that cold stars are dim. But it does get a little surprising when you go to different parts of the graph. Check this out. Okay, what if we end up with a star right here on the graph? What's that star like? Well, that star would be very, very hot. It's right above the O, right? It's on the hot side of the graph. The left is hot. But it's dim. And let's think back to what we said in some of these previous videos. If you look at the past couple of videos, if there's a star that's very, very, very hot, but still dim, that must be a small star, okay? That means that all of the stars in this corner, because they're hot, but they're still dim, that means that they must be small. So if you find the properties of a star and put it on this graph and it ends up down here, you know that it's got to be a small star, okay? So boom, that's a clue about that star. So let's do this. Let's write down in this corner, this bottom left corner, small. And you might be able to guess where I'm going with this. There's another place on this graph where we can find another size. Check this out. What if we go way up here? If there was a star that ended up, because of its properties, on this part of the graph, look down there. We're in the cold part of the graph now, right? We're in the cold part of the graph. But what's our luminosity like? Well, if we look straight over that way, we're going to hit the top of the we're at the top of the graph, so our luminosity is high. So stars that end up here are going to be cold, but still give off a whole ton of light. Their luminosity is really high. And what's the only way to do that? Well, it's the reverse of what we were talking about down there. If you're up here, if you're cold, but you're still giving off a ton of light, you must be big to make up for the fact that you're cold, okay? So, again, if you want to give off a lot of light, you could either do it by being hot or by being big, okay? So, check this out. This corner, stars that end up in this corner are big. So, even though this was a graph of luminosity versus surface temperature, this graph also is a way to figure out what size of star you're dealing with by where it ends up on the graph. So again, luminosity increases as you go to the top, surface temperature increases as you go to the left, but size starts small down here and then gets bigger as you go diagonally up the graph. The biggest stars are always going to be way up here, and the smallest stars are always going to be way down here, okay? And that also means that I can add something onto this graph real quick. Check this out. Here we go. Let me just add some diagonal lines onto it. If my pen works. There we go. And there we go. Now, what have I done here? What have I added to this picture? Well, again, remember, we said that stars that are down here are small, and as we go in this direction, we get bigger and bigger and bigger and bigger. So you can almost think of it as we cross these lines, we get bigger, we get bigger, we get bigger. What these lines represent are sizes. So the closer you get to this corner on the upper right, the bigger you get. So that means that any star on one of these diagonal lines are all roughly the same size, okay? So if we had two random stars on here, like let's say there was a star right here, and there was another star right here, then I already know that those two stars are the same size, right? Those two stars are the same size because they're on the same diagonal line here. But I know that a star that ends up on this line would be bigger than both of these because it's on the next line that's closer to the big corner. Every time you go to the next line, you're bigger than the stars before. And then if there's a star down here on this line, it's smaller than both of these. Okay? So, now, what are we talking about here? We're talking about putting stars onto this graph. So let's say we decided to take every star that exists, every single star that exists in the entire universe, like all billions and billions of them, and we decided to put every single one of them on this graph at the exact same time. Every single one of them. Like we went out, we measured, or we figured out their surface temperature and their luminosity and put a single dot for every star that exists. What does it seem like this graph would look like if you put every single star on here? It seems like it would just cover up the whole thing. You just have a full graph because you're putting billions of stars on there. But it turns out there's only a few combinations that stars can have. Turns out certain areas of this graph, there's just no stars with that combination, or at least so few that you wouldn't really notice it. In fact, 90% of stars show up in the same general area, and that area looks like this. It's roughly a diagonal line, not perfectly. There we go. Let me just kind of shade that area in. 90% of stars fall into that region of the map, that region of the graph, the diagram. So almost all stars have a combination of surface temperature and luminosity that lands them in this part of the graph. 90% of stars. And our sun is actually in there. You guys remember our sun is a G star, right? So our sun would be in this sort of swath here, right above the G. In fact, that first dot I drew, that's roughly where the sun would be on this graph. Now, we call stars that end up in that region the main sequence. Main sequence. So all the stars that end up in that region are called the main sequence. So our sun is an example of a main sequence star. What are main sequence stars like? Well, everything we said about what the sun was like, that's what these guys are like. Some of them are brighter than us. Some of them are hotter than us. Some of them are dimmer and colder than us. But in general, they work like we said the sun works. Okay, they've got hydrogen fusion in their core. That's what all of these guys are doing. But that's only 90% of stars. So where are the rest of them? 9% of stars end up down here in this general area. Somewhere around here. And if I do that, check this out. Here we go. Let's see what these stars are like. Well, what's their temperature like? Well, they're on the left. They're mostly O and B. These must be hot stars. But they're very dim. And they're towards the small corner. So their name comes from the fact that they're very hot, which would give them a bluish-white color, and their size, which makes them very small. These stars are called white dwarfs. They're called white because their temperature gives them a bluish-white color, and they're called dwarfs because they are small, okay? And that's 90% main sequence, 9% white dwarfs. That leaves 1% of stars. So this last type is rarer than the other types. And they're going to be up here. Okay. And this part of the graph is, well, what's the size like? What's the size like in this area? Well, we're really big. So this area is typically called giants, but sometimes is divided into two parts or two general areas, the giants and the supergiants, depending on how big they are. Although frequently these are considered to be the same thing and just called giants in general. On your GELO assignment, they consider these both to just be called giants. But later in this semester, we're going to be separating the two. But check this out. Later on, we're going to find out that these different regions of the graph are actually different stages of a star's life. Okay? The main sequence is the main part of the star's life. We know it lasts the longest because 90% of stars are in that stage. And then, as you'll see in later videos, after a star starts to die, it very briefly goes through a stage of its life where it's really big. Some of the main sequence stars become giants, some become supergiants, depending on certain properties we'll talk about. And then when a few of these stars fully die, one type of dead star you can become is a white dwarf. Okay? Don't worry too much about the life cycle stuff right now. That's coming in the next video, starting in the very next video. Now, that's basically the HR diagram. Okay? Important things to remember again are where are the bright stars? At the top. Where are the dim stars? At the bottom. Where are the hot stars? On the left. Where are the cold stars? On the right. Where are the small stars? Towards this corner. Where are the big stars? Towards this corner. Now, I'm not quite done, but I'm almost done. I do want to show you, this is the one that I drew, but I do want to show you the one that you're actually going to use in your GELO assignment. Looks like this. Where did it go? There it goes. There it is. So this is another HR diagram. It works exactly the same. It's a little bit squished. But it basically is the same thing. This side over here is luminosity. This side down here is surface temperature. Even though they've written different words, an HR diagram is always surface temperature down here and luminosity over here. What they've done is they've just written what units they're using, okay? Now, what they're using on this graph is the magnitude system, which if you didn't see in a previous video, make sure you go back and read up on that. In a previous video, we talked about apparent magnitude, and I talked about how I hated that it was upside down, where low magnitudes meant bright and high magnitudes mean dim. This is the same thing, except for it's called absolute magnitude, because instead of talking about how bright something looks, it's talking about its luminosity. So this right here is using the magnitude system for luminosity, but it works basically the same, okay? So notice the low numbers are at the top where it says bright, because low magnitudes mean bright. So just like we said before, bright is the top of the graph, but that means low magnitudes are the bright stars at the top of the graph. And down here we have our highest magnitudes. 15 is the highest one on here. But notice that's where we have the dim stars. So a high magnitude means a dim star. So all the stars along the bottom are dim, okay? Now down here, surface temperature, okay? Spectral class, that's the same thing as spectral type. So they've got O above hot, B, A, F, G, K, M. So that's working just the same as before. Cold on the right, hot on the left. And so also, just like before, that means the stars down in this corner are tiny, right? This is your small corner. Your white dwarfs are down here. Whereas up here, you have your big stars. Your giants are over here in this corner. And your main sequence would, again, start up here and go roughly diagonal down to this side. So that's basically the exact same thing as before. But there's one last detail I want to point out before I end this segment. If you look above the spectral types, you've got these little numbers. This says 05, and then you got just a 05, 05, 05, 05, all the way down. And eventually down at the end, you got this M9. So what do those mean? Well, remember, O, B, A, F, G, K, M, those represent temperatures. But those are only 7 temperatures, right? That's only 7 temperatures. And there's a lot more temperatures that stars can have, right? So what we do is we break up each one of these letters into 10 numbers. So there's an O0, an O1, an O2, an O3, an O4, an O5, and so on, all the way up to O9. And then you have B0, B1, B2, B3, B4, B5. So this is an O5. This is a B0, B5. So if you had a star that was a B2, you would place it between the B0 and the B5. This is an A0 and an A5, F0, F5. So that means the lower the number for each letter, the hotter it is. So a B0 is hotter than a B5. A G0 is hotter than a G5. If you had a star that was a G7, you'd put it right around here, because that's G0, G5, G7 would be before you get to the next one. So essentially what you're going to have to do on the GELO assignment is it's going to give you a set of stars, actually 2 lists of stars underneath a picture like this, and it's going to ask you to put all of those stars onto the graph. And all you got to do is it's going to tell you a spectral class and a magnitude for each star. So for example, let's say it said that you were dealing with a B2 with a magnitude of 10. Well, down here, this is B0, this is B5, so a B2 would be right here. So I know that my star has to be above the B2 mark. And I said it had a magnitude of 10, so I'd just go up until I hit where the magnitude of 10 would be. So a B2 with a magnitude of 10 would show up roughly where my finger is pointing. Our sun is a G2 with an absolute magnitude of something around a 4. Okay, so 0 to 5, 0, 1, 2, 3, 4 is just before you get to 5. So that's why the sun ended up right there. Okay. And remember, your GELO activity is guaranteed extra credit points. So give it a try. Do your best. It is required. So be careful about that. Okay? All right. And check the announcement for more information about that. See you guys in the next video. Rewatch this video right here as many times as you want while you're trying to do it. If you go through this video right here with a fine-tooth comb, you will be able to get the answers to almost everything on that assignment, that GELO assignment. It can give you extra credit for test 2, okay? And it also counts as a homework assignment. So